Question that we're going to address in this video is about the convergence of Fourier transform on the conditions under which the Fourier transform exists. So, what condition does a continuous time signal xt has to obey so that the Fourier transforms are guaranteed? So now, in the previous video, you would have seen that we have argument that the argument that we use in deriving the Fourier transform pair was that we assumed that xt was of was arbitrary but finite duration. But Fourier transform pair equations, they remain valid for an extremely broad class of signals of infinite duration. So if this representation has to be unique, that is, there is a one-to-one mapping between xt and its Fourier transform pair, well, this representation has to be valid for an infinite duration signal as well. Okay, so xt could be periodic signal for as well. So that doesn't mean the Fourier transform doesn't exist. They do exist, but now there are certain conditions that for which we have to see whether its existence is guaranteed or not. So in fact, our derivation of Fourier transforms suggests that a set of conditions like those required for the convergence of Fourier series should apply here, and indeed that can be shown to be the case here as well. So specifically consider xj omega and let xt denote the signal obtained by using xj omega in the right hand side of the following equation. Now you see over here, in terms of complex exponentials for a certain aperiodic signal, the strength is xj omega by 2 pi into d omega. You can see that how it is. Okay. Now this representation, how well does this compares? This is x tilde t. How well does this compares with xt? Is the question that we desire to answer. Okay. So under what conditions this representation is exact? So what we would like to know is when the above equation is valid, that when x tilde t is a valid representation of the original signal xt. Okay, so you see what we are doing is we are trying to recover supposedly our original signal from the envelope of the Fourier coefficients. Okay, so well, this question can be answered both ways. Either you can go in the forward direction or you can go in the reverse direction. Okay, so the first thing is whether if you go in the forward direction, is it guaranteed that xj omega exists? Well, if xj omega exists, then its inverse has to exist. Okay, so it has to be vice versa. So that existence is first of all satisfied if xt is of finite energy. So if xt is finite energy, that means it is absolutely square integrable. That is, xt is of finite energy. Xt could be of infinite duration period signal. Okay, but in one period, its energy should be finite. Okay, its energy should be finite. So it means if it is square integrable, then that would imply, if for finite energy, that xj omega is finite. So it is guaranteed to have Fourier transform, and that the inverse Fourier transform also converges to xt. Well, if the Fourier transform exists for a finite energy signal, then it is guaranteed that x tilde t is an exact representation of xt in the minimum energy sense. Okay, because the error that we are defining over here, et, is denoting the error between x tilde t and xt, is x tilde t minus xt. Okay, so the energy of the error goes to 0 when we are considering a finite energy signal. So thus, in a manner similar to that of periodic signals, or in Fourier series, you remember, if xt has a finite energy, then although xt and its Fourier representation x tilde t, they may differ significantly at individual values of t, which was the case in the which was much of the case in the discontinuities, but in the function. But there will be no energy difference. There will be no energy difference. You see, energy difference is 0. Okay, and those are the practical signals we are going to deal with, because finite energy signals are what we are dealing with most of the time in this course as an input to the LTI systems. So in terms of energy, there will be no difference. Okay, so x tilde t will be xt in terms of 0 energy difference. Okay, provided that x of t is absolutely integrable. Okay, or x of t is a finite energy signal. Then there are other conditions. So just as with the periodic signals, there exists an alternate set of conditions which are sufficient to ensure that x tilde t is equal to xt for any t except at discontinuity. So where it is equal to the average value of the either side of discontinuity. So if you recall, if xt has a discontinuous signal, like in a square pulse waveform, Then in Fourier series representation, when we were representing this by Fourier series, you recall there was ringing over here, okay, and then there was overshoot and undershoots, right? So at exactly the point where the function is discontinuous, the function is discontinuous, this value at discontinuity is the average of the point above and below the discontinuity. Okay, so that's the average of this point, and this happens at both sides of the discontinuity. So at discontinuity, the Fourier series representation is not the exact representation of the signal itself. Nonetheless, it's a very good representation, but it's not exact at the discontinuities. Okay, so but then we have those conditions, and we're going to see these conditions again in they're referred to as Dirichlet's condition for Fourier transforms. So for convergence, we require that besides finite energy, we require that xt must be absolutely integrable. If xt must be if xt is absolutely integrable, then that implies your Fourier transform exists. Well, this is not very difficult to see. You recall that your xj omega, which we have defined as the envelope of the Fourier coefficients, which is given as xt e to the minus j omega t. Okay, that was the definition of the Fourier transform of xt, or Fourier transform integral of xt, or you can say the envelope of the Fourier series coefficient, whatever. These are all the same terminology. So if you take the magnitude of both sides, okay, then the right hand side of this equation is less than or equal to the absolute of the magnitude of the integrand, okay, which is xt. Then we can bifurcate this into two magnitudes, e minus j omega t dt. Okay, so this is dt is a finite quantity, it's a finite difference. So this is still less than equal to mod of xt. Why? Because the magnitude of exponential is 1. Okay, so you see, if mod of xt over here is less than infinity, if that is the case, then it is guaranteed to have a finite magnitude envelope of the signal or the Fourier transform of xt. Okay, so the other condition we have besides the absolute squareability, absolute square integrability of the signal xt should be absolutely integrable. Okay, these two conditions, one can follow from the other as well. So if that is the case, then what this condition implies is that your Fourier transform xj of omega is going to be finite. Okay, that is the magnitude of xj omega is not going to be infinite. The integral is not going to diverge. X of j omega is the integral is going to converge. So a Fourier transform exists, and if the Fourier transform exists, then the inverse of Fourier transform, we have one-to-one mapping. That means x tilde t will be the representation of xt itself. Okay, so we can recover xt back given the Fourier transform exists. Then the second condition is that xt have a finite number of maxima and minima within any finite interval. Just like we have this condition in Fourier series, the number of maxima minima has to be finite. Okay, so if xt have a finite number of discontinuities within any finite interval, and furthermore, each of these discontinuities must be finite. Okay, so discontinuities should not be infinite. I mean, the number of discontinuities, for example, a signal having a function like this is going to have an infinite number of discontinuities is not allowed. Okay, so for a signal like this, the Fourier transform is not going to exist. Okay, if it continues like this, there are many discontinuities. So for such a signal, if it is periodic, even, I mean, the idea is whether it is periodic with certain period t, and then it is repeating itself again like this. Since the Fourier series is not existing because we cannot find the Fourier coefficients to be finite, there is no Fourier series representation. that means the envelope is not existing. That means if we cannot find a case, if we don't have a case for this, then this implies that your Fourier envelope xj omega is existent as well. Why? Because these Fourier coefficients happen to be the samples of xj omega. So if you have many discontinuities in a signal xt, you cannot find the Fourier coefficients, they are not finite, then xg omega is not there. Okay, you don't have it. So therefore, absolute integrable signals that are continuous or that have finite number of discontinuities have Fourier transforms. So absolute integrable signals or finite energy signals that are continuous and have a finite number of discontinuities, not infinite number of discontinuities like this case, like in this case what we have seen, because the Fourier series is not existing over one period, right? And if you, well, what you do is, if you tend t to approach to infinity, make it aperiodic, you don't have the envelope, you don't get the envelope, okay, because you don't get a case. That's the intuition. So although the two alternative set of conditions that we have been given are sufficient to guarantee that a signal has a Fourier transform, we will later see that the periodic signals, which are neither absolutely integrable nor square integrable over infinite interval, can be considered to have Fourier transform if impulse functions are permitted in the transform. Okay, so I mean, you have seen before as well. I told you that if xt is periodic, which can be represented in terms of Fourier series, coefficients, AKs, and harmonically related exponentials, where AKs are the magnitude of the strength of the harmonics contained in the signal, then Fourier transform, well, Fourier transform does exist for a periodic signal as well, but this exponential signal, you see, is of complex nature. Okay, it's not a symmetric signal like cosine or sine omega t, for which the Fourier coefficients are also symmetric, or for which the Fourier transform, for that reason, will also be real and symmetric. But for these signals, which are neither absolutely integrable nor absolutely summable, for example, for such signals which are periodic in nature, representing in themselves in terms of these exponentials, ej k omega naught t has a Fourier transform of delta of omega minus k omega naught. Okay, and if you're going to sum this up, then that means x of omega, the envelope, will be of the form equals to ak delta of omega minus plus minus, doesn't matter because k is varying from minus infinity to plus infinity, plus minus k omega naught t. So you see such functions which are, for example, delta t in xt over in this case is periodic signal, so it's of infinite duration in general, and it's not absolutely integrable, right? From minus infinity to plus infinity, you don't have absolute integrability of xt given it's periodic, and neither it is square integrable. So for such functions, you will see that the Fourier transform will exist, although these are sufficient conditions, absolute integrability and squareability, but these are not necessary conditions for such signals which are not absolutely integrable, neither square summable, neither square integrable. You will have the Fourier transform in terms of the impulse functions. Okay, we are going to consider them in much details later on. So, but for now, for such functions, we will have impulse functions in the transform domain, in the Fourier domain. Okay, but again, these conditions that we have discussed are sufficient. Okay, these conditions, absolute integrability, finite energy, are sufficient conditions to show that the Fourier transform exists, but these are not necessary conditions. These are not necessary and sufficient conditions. Okay, so that's all.